the reason for looking at this, some of this is review because you've been reading about it in your reading assignments. You did a stations activity with these concepts, but we're going to review them again today and build on that a little bit. And we're also going to do foreshadowing of the next unit. So remember, we have a test on Friday, and so today's the 6th. That would be Friday the 8th. And then we'll have another test either at the end of the following week or the Tuesday after that. So, ionic bonds. Ionic bonds are always involving a transfer of electrons from a metal. Is that showing on the screen behind me? So if you see an equation that's a formula, chemical formula, it starts with a metal, immediately you know that it's ionic. And ionic compounds are always a metal combined with a nonmetal. And you guys know examples of this. You know that sodium chloride, that's the one everybody just kind of has memorized. But there are lots, there's calcium chloride and there's magnesium chloride and there's iron chloride, and the list is really long. Now, the metal always gives up electrons, and the nonmetal always takes electrons, right? That's how ionic compounds are formed. And then they are held together by those positive and negative forces. The positive charge of the cation and the negative charge of the anion. And we're going to touch on Lewis structures, although you don't really have to know how to do them. No, that's not quite true either. We're going to touch on Lewis structures, and we're going to touch on naming. The naming comes next week. It's not on Friday's test. The naming part is foreshadowing next week. So let's look at rubidium fluoride for a moment. Rubidium. Which column is rubidium in? So how many valence electrons? One. That's rubidium. Let's look for a moment at fluorine. I'm going to just make fluorine something like this blue color maybe. Fluorine. What column is fluorine in? And how many valence electrons does fluorine have? How many? So, since we have a metal and a nonmetal, what is going to happen here is the electron from the metal is going to be transferred to the nonmetal, and that's going to leave us with a rubidium ion, right? A cation, and a anion made of fluoride. We will call it fluoride now that it has a charge of -1. Now, the next thing I'm going to write is the formula as you would write it. We're just going to write RB because there's one of those. The metal is always first. The nonmetal is always second. And the name would be rubidium, always metal first, fluoride. I love spelling fluoride. Rubidium fluoride. Now, That's pretty simple. Now, by the way, on Friday's test, you'll need to be able to show what I'm going to show you next, how these electrons transfer to make the compound. Because like right here for sodium and oxygen, that's not the formula of the compound we're going to have for sodium and oxygen. So let's write sodium. How many valence electrons does sodium have? 1 is correct. I'm going to just switch to red for oxygen because I like doing oxygen in red. How many valence electrons for oxygen? Yes. Sorry, that should be Na. Good catch. Oxygen, 6 valence electrons. And I'm going to choose to put them 1, 2, 3, 4, 5, 6. You don't want to end up with more than 2 electrons on a side. The reason I do it like this is if you looked at the P sublevel and you started filling in electrons, you'd have 2 sides that only had 1 electron. That's my rationale for the way I'm drawing it. So this electron from sodium transfers over here to fill this spot. But we have a problem because the octet rule says oxygen needs 8. And if there's 1 sodium atom around, there's probably going to be a septillion others. So that just means another electron is going to come from this sodium and fill that spot. So that's going to result in sodium ions with a charge of +1, and that's going to result in oxide ions with a charge of -2. But when we write the formula, we're always going to put the metal first. But how many sodium ions did we make, actually? We made 2. But we're not going to write 2Na in the formula. No, we're going to write Na subscript 2 to show that we have 2 sodium ions. And we're going to write oxygen to show that we have 1 oxygen. And the name of this compound, and this is where we're going to come to this next week, not this week, but this will be sodium oxide. So we just have the cation and the anion. So if only it was always that simple. It's pretty simple right now. Cation, anion. Can I go to the next formula? Here we have calcium, the metal, with 2 valence electrons. Phosphide. How many valence electrons in phosphorus? Does 5 look right?
Oh, wait. I'm done.
So a calcium ion is going to go fill out that orbital. A calcium ion is going to go fill out that spot. Uh-oh. We need more calcium. So here's calcium with its 2 valence electrons, and that's going to transfer here. Oh, now we need more phosphorus. So This electron now has a place to go. Ah, no. We need one more calcium. This is going to work out this time.
Yep.
We're going to fill this spot. We're going to fill this spot. Now, every atom is more stable because we've made calcium 2 plus ions, and we've made phosphorus 3 minus ions, and everything is happy. Now, when we write the formula, how many calciums are there? 1, 2, 3. How many phosphorus are there?
Yes.
Ichini. You guys out there showing off your counting skills. Okay. Now, would you guess the name of this is pretty easy? We just write the cation and the anion. Calcium phos. What are you going to write after the H here? What was after the I up above? These are all going to end in IDE if they're monoatomic anions, calcium phosphide. So, turn the page. We're going to do these a little bit quicker. You know there are several kinds of covalent bonds, but they all come between nonmetals and other nonmetals. These are always formed by sharing electrons. They're all formed by sharing electrons. And like if you have a pair of electrons where one of those electrons is from this atom and the other electron is from this atom, this positive nucleus is going to attract the electrons, and this positive nucleus is going to attract the electrons. So once again, they're held together by the attraction of these positive and negative charges. So we're going to look at these a little bit faster. You don't really need to know for this coming test. You don't need to understand how to do the Lewis structure. In fact, I think I'm going to sketch it really quick. Carbon can form 4 bonds. Oxygen can form 2 bonds. So carbon forming bonds with 2 oxygen is going to end up like this. Now, this positive charge from the oxygen nucleus, the carbon nucleus, and the other oxygen, they're going to cause an attraction between these particles, and that's what those double bonds do. Now, you have studied a little bit about bond energy, and that if you're going to break those bonds apart, you know how much energy you have to put in. You also know that you have to break these bonds apart, and it's going to take a lot more energy because there are large charges involved holding those together. And that was all in the stations activity you did a while ago. Oh, name. Once again, this is a different kind of compound, so it's going to have a different naming system. And we'll learn this next week. This is kind of foreshadowing that if we have CO2, its name is going to be carbon monoxide. Oops, not mon. That would be carbon monoxide would be CO. How many oxygens are there in this compound? So what's the prefix that's going to be used? Dioxide, yeah. And what about this one?
Oh my god.
This one's going to be hydrogen.
Dioxide. Di.
No, we've got to have a prefix here, right?
Dihydrogen. Oh my god.
Dihydrogen. How many oxygens?
One. Monoxide. Mono.
So you notice we did not put a mono in front of carbon here. We'll learn more about that next week. We'll focus on that a little bit next week. And I think we're going to focus on this next week as well. Let's get to the rest of today. So I'm going to close off this video